Namaste. Welcome to Dr.ARM's chemistry. We were discussing the theories of acids and bases. We have seen number of such theories such as Arrhenius theory and Lorentz-Bronsted theory or Levy's concept, etc. And now we are discussing the methods to measure the strength of acids and bases. So in that case also we have seen number of such methods, and presently we are going to see here the next method for the measurement of acidity, that is acidity of cations in aqueous solutions. So when the cations are in higher oxidation state, then when they are taken in the form of aqueous solution, they are behaving as acids, and their solution, for example, if we take means the solution of such ions is having specific color or it may be colorless depending upon the concentration of the acid or the pH of the solution. For example, if you consider Fe3+, so this is transition metal with higher oxidation state, and when it is dissolved, when the salt is dissolved in water, it gets hydrated, and depending upon the concentration of the solution, it forms the hydroxides or sometimes the oxides. So depending upon the concentration of that metal ion, the color of the solution is observed. So we will see how the hydration of the metal ion is taking place, and the resulting weaker base, how does it behave and give further reactions. So for example, we will see this as Fe H2O 6 3+. So when it is dissolved in water, means when the ion is metal ion is added to water, it gets this hexaquaphor complex, and it gets dissociated in this, giving you the Fe H2O 5 OH 2+ with the formation of H3O+. So here you will find that this is hydroxide and it is weak base. So this is acid, this is weak base, that is hydroxide. So this is conjugate acid-base behavior as we have seen in the Lorentz-Bronsted concept. So this is acid and its conjugate base. Further, this again undergoes second Fe H2O5 OH 2+. Further forms more hydroxide, means more basic compound like this Fe H2O4 OH twice plus H3O+. So this is weak base, and further this is again more weak base. So here higher oxidation state of this Fe, Fe favors or promotes the loss of H plus from one of these H2O, and therefore the strength of the acid is exhibited in this way. So here we find that the acid is converted into weak base, and again this weak acid is further converted into still more weak base. Then if the solution is less acidic or more basic, then this compound also gives us the hydroxide or the oxide form. So this reaction is observed here. We can observe this reaction with the formation of a bridged structure, bridging with the use of such the OH minus ions and oxide ions. So we can show here the reaction as twice Fe H2O 5 OH H2O 5 OH 2 plus gives us the H2O4 OH plus twice H2O plus twice H2O. So this is called bridging. So this type of bridging is observed when the solution is more basic. And such solution gives us the measure of or understanding of the acidic strength of the cation. If we see the other cations, if you see the other cations such as say alkali metals, metal ions, then these are not acidic, means they are showing no acidity. Then if you see another, that is alkaline earth metals, alkaline earth metals, metal ions, so they are having slight acidic, they are having slightly acidic, slightly acidity or slight acidity, you can say these are having showing slight acidity. Again, if we see the transition metals, then transition metals with 2 plus state, they are weaker, weakly acidic. They are weakly acidic. Then if we see the transition metals in plus 3 state, they are relatively more acidic. We can say moderately acidic. And transition metals with plus 4 or more oxidation state, they are strongly acidic. So in this way, the acidic nature of these various metal ions are observed. So here you will find that the transition metals having +3 or more hydroxidation state, the cations are exhibiting their acidic nature, so they are acidic. So this acidity is considered in terms of their Ka values, dissociation constants or equilibrium constants. So we can show these metal ions, that is Fe3 plus, Cr3 plus, Al3 plus, and scandium 3 plus. Scandium 3 plus. Now if we show the Ka values, then the Ka values are higher here, 6.7 into 10 raised to minus 3. Then the next has 1.6 into 10 raised to minus 4. Then aluminium has 1.1 into 10 raised to minus 5. This has also 1.1 into 10 raised to minus 5. Then these are higher oxidation states. Now if we take the oxidation states of other metal ions, that is Fe2 plus, P2 plus, then Zn2 plus, Cu2 plus, Cu2 plus, then Ni2 plus, Zn2 plus, etc. Then their Ka values are like this. Fe2 plus has 5 into 10 raised to minus 9. This has 5 into 10 raised to minus 9. This has also 5 into 10 raised to minus 10. And this has 2.5 into 10 raised to minus 10. So they show that the higher oxidation states are having comparatively stronger dissociation constants or equilibrium constants. So which shows that they can be easily dissociated. Then we can generalize the reaction for the dissociation of the cations in water and formation of the hydrated cations, hydrated hydroxides. For example, generalization will be like this: metal MH2ON in charge is N plus. So when this is dissociated, dissolved in water, then here it is N. Then this will produce the MH2O, M minus 1, and OH. Here N minus 1 plus N H3O plus only one, not N, only one H3O plus. One OH is just a transparent. So the hydroxides of these metal ions are formed in this way, which shows the acidity of metal cations. So this is one aspect. Then these metal hydroxides are also studied or considered for their acidic behavior or acidity in terms of the solubility of hydroxides. The stronger metal cation acid is less soluble, has less soluble its hydroxide. For example, if you see the Fe3 plus, it is yellow color or brown yellow colored solution. When the concentration of that solution is very high, then the detection of the cation is also very less, and in that case the solution shows precipitation of the hydroxide. And if we add, means when the solution is neutral or weakly basic, when the solution is neutral or weakly basic, then the hydroxides are formed. But when we add any acid to that solution, the precipitate which is formed gets dissolved and the color of the solution is pale. Or after increasing the acidic nature or strength of that acid, means if we add more acid to that solution, then the solution becomes, means color of the metal ion is becoming nearly colorless. So in this way, we can consider the example of Fe3 plus, as we have seen that it is yellow color when the metal ion concentration is very high in the weakly basic solution or slightly acidic solution, then it is, or neutral or slightly weakly basic solution, then the precipitate is formed, means aggregate of the hydrated hydroxide is formed, but it gets dissolved after addition of acid. Similarly, if we see the D block metal ions and Mg2 plus, D block metal ions and Mg2 plus, this shows that the precipitate as the hydroxide is formed in the precipitate of the hydroxide is formed even in the neutral or weakly basic solution or slightly basic solution. Then if we take the alkali or alkaline earth metals, then the hydroxides of that metal ions are weakly soluble, means they are not showing any effect of pH, means pH change is not detected in the hydroxides of these alkali and alkaline earth metal ions. Then if we take these some examples such as metal hydroxide, we can take this metal hydroxide, now we can consider its Ksp value because we are considering the precipitation. So the FeOH thrice, then we are considering here Ksp value, solubility product values. So you will find that in case of FeOH thrice, the value is 6 into 10 raised to minus 38, 6 into 10 raised to minus 38. Then another hydroxide, CrOH thrice. So its Ksp value is also nearly the same. It is 7 into 10 raised to minus 31. Then third hydroxide is aluminium, AlOH thrice. This is also nearly equal, 1.4 into 10 raised to minus 34. Now Now if we compare this with the metal ions which are having +2 oxidation states, that is, if we consider this FeOH twice, then we will see CuOH twice, CuOH twice, then nickel NiOH twice, then zinc ZnOH twice, then MgOH twice. So these are various hydroxides and their Ksp values. So Ksp values of these are like this: 8 into 10 raised to minus 60. In case of CuOH twice, it is 2.2 into 10 raised to minus 20. In case of nickel, it is 2 into 10 raised to minus 50. In case of zinc, it is 7 into 10 raised to minus 80. In case of MgOH twice, it is 1.1 into 10 raised to minus 11. So these are the solubility products which explain the possibility of the formation of their hydroxides. So these values shows that these hydroxides are very easily formed compared to these hydroxides because their Ksp values are very low, and here these are having higher values of solubility products. Then if we see the highly charged metal cations, if we see the highly charged metal cations, then we find that they are having oxidation states +7, +6, +5 or +4, etc. And they are showing their behavior like this. So for example, if we take this manganese MnO4 minus, then Cr2O4 2 minus, then another is VO2 plus, VO2 plus, VO2 plus. So these are various metal cations or vanadium. So these are UO2 plus one more UO, plus uranyl ion, UO2 plus. So this is UO2 plus uranium. So here they are showing +7 oxidation state. Here we will find that +6 oxidation states, +5 oxidation states, +4 oxidation states are observed here. And out of these, if we take the two examples, MnO4 and Cr2O4, these are having strong, they are having strong oxidizing power. When they are used in acidic medium, they are behaving as strong oxidizing agents. This is because these ions are very weak bases. these ions are very weak bases, and their Ksp values are relatively lower. Now you will see here, if we take the example of dichromate ion, Cr2O4 2 minus dichromate ion, so plus H plus. So this is weak base. When it is added with H plus, then it gives HCrO4 minus. Then so you will find that there is Kb value, dissociation constant for the weak base. So this shows that the value is 3.2 into 10 raised to minus 8. And again, if we take this HCrO4 minus plus 1 over H plus, it gives us H2CrO4 having Kb. So this has the relatively less value, 5.6 into 10 raised to minus 14. So these values are compared to this value is lower, and it shows that in concentrated acid the dichromate ion formula is showing loss of water. So we can show this reaction here. When we use concentrated acid solution, the dichromate ion formula H2CrO4, we will take this HCrO4 minus, so this will lose one water molecule and it gives Cr2O7 2 minus Cr2O7 2 minus plus H2. So this is showing the loss of water when the concentration of acid is increased. So in this way we can observe acidic nature or acidity of metal cations in higher oxidation states. So we will stop our discussion. Please subscribe to this channel and press bell icon and like button. So thank you very much for watching this